online monitoring, we are trying to use Raman spectroscopy techniques to, to measure real-time accounting of nuclear materials, like a concentration of uranium, or a oxidation state, or gas composition like iodine. What is in the iodine concentration in the liquid state? What is the concentration of iodine in the gas phase? So we are trying to develop some of these online, techniques at PNNL. And also, we are also looking at advanced materials and membranes to capture xenon and krypton at much higher temperature as opposed to cryogenic distillation process. For example, currently they use a cryogenic distillation to separate the xenon and krypton, which is found to be too complex and also have a large footprint and costly. So we are trying to come up with the alternate materials to develop some of these separation techniques at much higher temperature. Amanda Lyons, basically she's building these Raman spectroscopic tools to measure the concentration of the iodine vapor in the solution as well as in the gas phase. So we did collaborate with the ORNL as part of this MSR campaign to to predict off gas and to identify the iodine composition. So, and also we are developing, supporting system development and demonstrations, and also trying to collaborate with the industry to develop this technology further. And also we have some opportunities to collaborate with the INL to measure the tritium or hydrogen isotopes. We are developing these new class of materials called metal organic frameworks, trying to replace some of the charcoals that are typically used in the pretty much nuclear industry. Again, the reason we want to develop these materials was because these have high surface area. As a result, you can able to reduce the footprint of this off-gas system significantly. So we have done some kind of a scale up as part of the previous programs. We have characterized these materials. We have done some kind of a two-bed approach where we can able to remove the xenon in the single bed at room temperature, and we can able to pass the air without xenon to the second bed containing the same material or different material, where you can able to take out the krypton and the off gas goes to the stack. So as part of the MSR campaign last fiscal year, we did scale up the MOF material at a really a large quantity up to 10 gram scale. And we use this capability to measure the xenon krypton separation from the MSR off gases. And we basically predicted how well this MOF material performs in comparison with the charcoal material. Based on our data under exactly identical condition, this particular material can reduce the bed volume by roughly around 50 to 60% in terms of bed volume. So likewise, we send this material to our Oak Ridge National Lab to incorporate this MOF material into the LIPS technique. So we have MOFs here, and Andrew Hunter basically look at the a LIPS measurement to validate our results, what we have done at PNNL. And also apart from these engineered particles, what we have here, we also collaborating with the ExoDis on the same class of material, but we are trying to use the MOFs as a membranes as opposed to engineered beads. So here is just alumina support. We grow a thin film of MOF on top of this material by a layer approach, and we are putting these membrane disc in between these two discs here, and we basically pass the xenon krypton gas mixture, and we basically measure what's coming out from the other side of the membrane. Again, like MSR, pretty much requires some kind of a waste treatment. So because you have these chloride and fluoride salts, due to the radiolysis of this chlorine and fluoride salts requires some kind of a treatment. So we have to remove these halogens through some kind of a dehalogenation process, and then partition those waste streams into different waste streams. So we have some options for chlorine treatment and waste forms, including glass and glass banded mineral waste forms, and halide gas capture at high interest using the zeolite and other class of materials, I would say. And lastly, last but not the least, we do have some kind of a radiation stability testing experiments at PNNL. We are planning to do some kind of a radiation exposure experiments on various class of materials next fiscal year, trying to understand if there is any radiolysis of these materials under the tested conditions. So we have the gamma source, cobalt-60, gamma radiation, and we have a neutron source. And we can also simulate wide variety of temperatures from anywhere from -20 to 200 degrees Celsius. At the same time, we can able to vary the humidity from 20 to 90% relative humidity. So we can able to test in a wide range of temperatures and the humidity conditions to measure the radiation stability. So I think with that, I would like to thank everyone.